Now next we are going to look at the divergence theorem. Remember when we started we said that there will be two theorems that we are supposed to look at which are very important in electromagnetic field theorem. And these are the divergence and Stokes theorem. So our divergence theorem. So maybe if I was to state that, it states that the integral of the normal component of a vector, the integral of the normal component of a vector over a closed surface is equal to the integral of the divergence is equal to the integral of the divergence of that vector throughout the volume V, enclosed by the surface S. So the integral of the normal component of a vector over a closed surface is equal to the integral of the divergence of that vector throughout the volume V enclosed by the surface here. So mathematically, and as a student, if you cannot be able to cram all that long statement, you can opt for the mathematical statement. So mathematically, we are saying that the divergence theorem can be represented as the divergence. Remember this, a vector dot another vector. We have that. We say that the normal component here, this is our normal component of this vector, must be equal to the volume integral of the divergence of that particular vector throughout the volume. So you can see now here, the circle with integration stands for an enclosed surface. This is our enclosed surface. So we have that to represent an enclosed surface. Then we have V to represent what? The volume in which the surface exists. Now, very simple here. The left-hand side is a double integral. The right-hand side is a triple integral. And remember our differential surfaces and differential lengths that we've just covered. So they will come in handy here and here. Hope when we'll be looking at some example, that will be very easy for us to look at. So the next theorem that we are supposed to look at is Stokes Theorem. And it states that the line integral of the tangential component of a vector A around a closed path L is equal to the surface integral of the normal component of curl of A bar, over the surface enclosed by the path L. So we can say again, mathematically, we can have the integral of This is our tangential component that, so you can see this is our closed, we are saying that our closed path, L being that, and it is represented as that, must be equal to the surface integral of curl of A dot ds bar. Remember, this again is a what? It's a surface integral, yeah? Curl of A dot that. If it is an enclosed path, you can just put that. This can further be rewritten as, and we have curl being represented as that dot ds bar. So that is how we represent our Stokes theorem mathematically. Maybe we can look at two examples related to these two theorems. We can go and look at two examples related to the theorem. And maybe we can have our first example here. Given that d bar, so our vector d bar is given as 10 the row of 3 power 3 row power 3 4 a row bar in cylindrical coordinates comma, then we can say evaluate both sides of divergence theorem for the volume enclosed. For the volume enclosed by rho is equals to 2, comma, z is equals to 0, and z is equals to 10. So now this is our example, a very good example that is a typical exam question, yeah? And the way we've stated our divergence theorem, actually when they're telling you to evaluate both sides of divergence theorem, is the same as prove the divergence theorem. The left-hand side to be equal to the right-hand side of the divergence theorem. So in our solution, we can make our statement. So we've said that the surface, the enclosed surface of a vector should be equals to the divergence of the volume of that particular vector. So if we have that now, we can say now, taking the left-hand side, so here in my solution, then I can say, taking the left-hand side of the divergence theorem, then we have that as our left-hand side. Now again, it's very important that we take note of the direction of our vector. Now if we look at our vector that we are given up here, the vector that is shown up here, it's very important that we take note of what? Its direction. It's only having a direction in the A row. Remember, this is cylindrical coordinate system. So it is my cylinder. If I have a cylinder, that is the center of the cylinder. Yeah, because it's cylindrical coordinates, then my direction is only in that particular direction. So it is A row direction. So we have flux density. Later on we'll realize that D is flux density that is working only on the surface. We don't have flux. Flux at the top and at the bottom of the cylinder is equals to what? D component at the top and the bottom of the cylinder is equals to 0. Same to this. We also have it as 0, but it is existing only on the surface of the what? Cylinder. So now, we can have that, and then again, very important now that we've realized that we only have flux on the surface of the cylinder, then we need to get that component of ds that was existing only on the, not only, but in the direction of A rho. It is important to find that differential surface that exists only in the direction of what? A rho. So let us look at that. So we can come back to our question and see. So if we represent that, we've realized that we don't have D in the top and the bottom, it's only in the surface, so we are only interested in the direction of A rho, then this can further be represented as, I can have the double integral, it's D in the direction of rho, it's only that, A rho, dot. So the dot here is this. This is the vector that makes that a vector. This is the magnitude, which is 10 A rho over 4, should be represented by D rho. Now, what is ds in the direction of A rho? So ds in the direction of A rho, if you go back to what we had find out that the differential surface in the direction of A rho will be the same as rho d phi d what? dz in the direction of what? A rho bar. So that is what we have. Then now, you see what I was telling you when we started, that S stands for double integral. So now I've indicated my double integral sign. What are the limits for my double integral sign? So limits for the double integral can now be indicated. And again, remember, in our cylindrical coordinate, our ranges of phi was ranging from 0 to what? To 2 pi. So if I was to indicate this, my limits for d phi will be from phi is equals to 0 to phi is equals to what? 2 pi. Then the limits for z are given in the equation. You see, we say that z can range from 0 to infinity. But here we are working with z is equals to 0 and z is equals to what? 10. So my ranges for z will be from z is equals to 0 to what? 10. Now, because we are only integrating with respect to phi and z, then rho is a constant. And again, in the question, the value of rho is given as rho is equals to what? 2. So let us do let us do our integral and see what we are going to get as our answer. Now, it's also very important to note that there is a dot product here. So if I dot A and another A, I'm supposed to get 1. So if I insert my values, then this value will disappear. A dot A is equals to 1, such that now we no longer have the direction again. So this translates into integral from phi is equals to 0 to 2 pi. Then from z is equals to 0 to 10. I was given d rho, and d rho in the equation is 10 all over 4. The rho value is 3, but there is also another rho, so rho becomes 4. Then I have the phi, d what? dz. d phi dz. So we've said, but rho, you can put that there, rho is equals to 2. So that we can take all our constant terms outside the bracket and simplify by substituting rho there. So this becomes 10 all over 4 instead of rho is equals to, and the value of rho is 2, so this will be 2 power 4. And then we can integrate. Here there is no order of integration. So integrating with respect to phi and with respect to z. So if I integrate with respect to phi, I'll have, d phi, I'll have phi from 0 to 2 pi. Again, if I integrate dz, I'll have z from 0 to what? To 10. Then I can do my simplification such that 2 power 4 is 16. If you cancel that, we are going to have what? 10 multiplied by 4 into 2 pi, because I've inserted the upper limit, the lower limit is 0, multiplied by 10. So if you multiply that, we have 40, 400. The answer becomes 800 pi. Now that is our left-hand side of our question. Then next, now we are supposed to look at the right-hand side. The right-hand side of that question, so that we can see if the divergence theorem is giving us the right value. So now, again I can say, taking the what? The right hand side. So if we take our right hand side of our divergence theorem, then we have the integral of div of d bar d what? dv. Now when you see a v here, then it means we are doing a triple integral. So we have that of div, the div of v, sorry, div of d, dv. And what is this dv? So again, it's very important to know our differential volume in cylindrical coordinate system. And our differential volume in cylindrical coordinate system was supposed to be rho, d rho. So instead of writing dv, we have rho, d phi, d what? dv. So that, sorry, d phi, dz. So that is what we have as our value of v. Then because I have indicated all this, then I can put my limits. So we have the values of rho. Rho should be from rho is equals to 0 up to 2. You see, we say that it can extend from 0 to infinity depending on the size of the cylinder. Then so rho is from 0 to 2. Then the next one is phi, and we have seen phi in the previous part as being from 0 to 2 pi. Then finally we have z, and z again is given in the question. Z ranges from z is equals to 0 to z is 10. Yeah? So this is from z being equals to 0 to what? To 10. So now let us get the divergence of our vector d. So the div of vector d, divergence of vector d. So now let us look at the divergence of vector d. So we are saying that the div of vector d. Now, very important to note, we must know the coordinate system. And we've said here, and it's also indicated in the question, that our coordinate system is cylindrical coordinates. So we need to know which formula are we supposed to apply. Yeah? The divergence of d in cylindrical coordinate system. So remember very well, when we had that, we say that the divergence of that should be 1 over rho partial rho partial rho of rho d rho. So now that is our formula that will help us get the divergence of this particular vector. And this now will translate into 1 over rho. Then we have partial rho into this rho multiplied by 10 rho cubic all over 4, like so. That rho together with this rho should give us one. We have that first partial rho 10 over 4. This to this will give us rho power what? 4. Rho power of 4. Now let us get the derivative of rho power 4, and if we do that, we are going to have what? 1 over rho. If we differentiate that, this value, we are going to have 10 over 4 first, that is a constant. Then rho power 4 will give us 4 rho what? Cubic, like so. So this and this cancels, and we are left with 10. And this, when you simplify that, we're going to have what? 10 of rho what? Squared. Now we have our divergence of the vector. So we want to insert this value to substitute this value here and multiplied with rho. So if we do that, we are going to get have rho is equals to 0 to 2, phi is equals to 0 to 2 pi, z is equals to 0 to 10. Then we have 10. We have rho squared times that gives you rho cubic. Then we have d rho, d phi, dz. So we can factor out 10 because 10 is not involved in the integration. Then we can integrate rho cubic, and if you integrate rho cubic, you'll get rho power 4 all over 4. Limits of rho ranges from 0 to 2. If I integrate d rho, d phi, I'll get phi. And the ranges of phi ranges from phi is equals to 0 to 2 pi. Similarly, if I integrate dz, I'm going to get z, and the ranges of z ranges from z is equals to 0 to 10. Then we do our substitution. So take this 4 out. If it simplifies that, I'll have 5 over 2. Then, rho power 4, substitute that, we'll have 2 power 4. If we substitute for this, we'll have 2 pi. Finally, if I substitute for that, I'll have 10. So, if we simplify this, we'll have 5 over 2 into 16 into 2 pi into 10. So further simplification, this translates into 5 multiplied by 8 multiplied by 2 pi and multiplied by 10, which gives you 400 times 2. This also gives you what? 800 pi. And so you can see our left hand side and the right hand side are giving us the same answers. Hence we've proved the divergence theorem, or we've evaluated both sides of the divergence theorem. So that has shown us that our left hand side and the right hand side are equal. So divergence theorem is true. Yeah. So we can look at another example so that we'll be able to show us whether Stokes theorem is also true. Yeah. So our example 2,